Good morning. Let me start with a question. How many of you have heard of quantum computing? And how many actually understand what it is? That's exactly why I'm here. After years spent diving deep into quantum computing, reading research papers, analyzing company strategies, and following breakthrough announcements, I discovered something fascinating. Most people think there's just one type of quantum computer, but in reality, there are 9 completely different ways to build these incredible machines. Today, I'm going to take you on a journey through all 9. No PhD in physics required, just curiosity and maybe a sense of humor. Because quantum computing is about to change everything, and it's way more fun than you think. To make this all click, imagine trying to cook the most complex, delicious, impossible meal ever. A meal so complicated, it would take a normal kitchen 1,000 years to prepare. Classical computers are like having one really fast chef with a sharp knife, but some meals are just impossible to make quickly, no matter how skilled the chef. Quantum computers, on the other hand, are like a magical kitchen where ingredients can be in multiple places at once, pots can stir themselves, and recipes can be tested in parallel universes. It sounds wild, but that's quantum mechanics for you. And here's the key. There are 9 completely different ways to build these magical kitchens, each with its own unique superpowers. Let's start with the speed demons, the Formula One race cars of quantum computing, known as superconducting quantum computers, which companies like Google and IBM have invested billions in. Imagine building a race car so fast it has to be kept colder than outer space to work, at temperatures 100 times colder than the coldest place in the universe. Why so cold? Because at those temperatures, electricity flows without resistance, like a racetrack with zero friction, letting quantum information zip around at incredible speeds. In 2019, Google's quantum computer achieved quantum supremacy, solving a problem in 200 seconds that would take the world's fastest supercomputer 10,000 years. Like finishing a Formula One race while everyone else is still trying to start their engines. The catch is that these machines are incredibly complex and expensive. But when you need raw quantum speed, nothing beats them. Now let me tell you about the Swiss watchmakers of quantum computing. Trapped ion quantum computers, built by companies like IonQ, take a completely different approach from the speed-focused superconducting systems. They go for precision. Imagine a watch so exact it uses individual atoms as gears, each one held perfectly in place by invisible electromagnetic fields and controlled by laser beams. Every gear in this quantum watch is perfectly identical, made by nature itself. And this natural perfection means trapped ion systems can maintain their quantum properties for minutes instead of microseconds, a difference like a steady spotlight compared to a lightning flash. While superconducting computers are like Formula One cars needing perfect conditions, trapped ion systems are the Swiss watches that keep perfect time for years. The trade-off is that they're slower than superconducting systems, but sometimes precision matters more than speed. But here's where it gets really interesting. What if I told you there's a quantum computer that works with pure light? Photonic quantum computers, built by companies like Xanadu, use particles of light, photons, as their quantum bits. Think about this for a moment. Light can travel across the universe for billions of years without losing its properties. It doesn't need to be kept cold. It doesn't degrade. It's naturally perfect for carrying quantum information. It's like building a computer out of rainbows. Sounds impossible, but it works. And here's the really cool part. Photonic quantum computers aren't just computing machines. They're the foundation for the quantum internet. Imagine sending information that's protected by the laws of physics themselves. Information that can't be hacked, can't be intercepted, can't be copied. The challenge with photonic systems? They're harder to control than other approaches. It's like trying to do surgery with laser pointers. Possible, but incredibly difficult. But when you need quantum communication, nothing else comes close. Now let me tell you about Microsoft's moonshot, topological quantum computing, the most ambitious, theoretical, and potentially revolutionary approach of all. Imagine building a quantum computer that's not just resistant to errors, but naturally immune to them. While most quantum computers are like balancing a pencil on its tip, with someone shaking the table, the slightest disturbance ruins everything. Topological quantum computers would be like tying your shoes. Even if someone bumps you or you make small mistakes, you still end up with tied shoes. Microsoft is betting on exotic particles that exist only in 2 dimensions, so strange that they remember every path they've taken, with that memory becoming quantum information. So it's like having a quantum computer where the very shape of space protects your data. The catch is that these particles are incredibly difficult to create and control. Microsoft has been working on this for over a decade and is only now starting to see real progress. But if they succeed, they'll have built the most powerful quantum computer imaginable. Here's an approach that I find absolutely elegant in its simplicity. Neutral atom quantum computers, like those built by QuEra, use perfectly identical atoms as quantum bits, each held in place by optical tweezers made of laser light. Imagine 256 identical marbles, each suspended by invisible hands, able to communicate instantly with every other marble. The beauty of this method is that the qubits are made by nature itself. No manufacturing defects, no variations, no inconsistencies. Every atom is exactly the same, because that's how atoms work. Unlike other quantum computers that require massive cooling systems or complex electromagnetic traps, neutral atom systems can operate at room temperature, making them naturally perfect and simple. The potential for scaling is enormous, with researchers already envisioning systems containing thousands of atoms. Imagine a quantum computer with the power of a supercomputer that fits on your desk. Now here's where my research uncovered something really exciting. Intel has figured out how to make quantum computers using the same factories that produce every computer chip in the world. Silicon spin quantum computers leverage the existing semiconductor manufacturing infrastructure, the same clean rooms, precision equipment, and processes perfected over decades. So imagine if quantum computers could be manufactured as easily and cheaply as smartphones. That's the promise of silicon spin qubits. Intel's quantum chips are 1,000,000 times smaller than other types of qubits, manufactured with a 95% success rate, and built with technology already proven at massive scale. It's like discovering you can build rocket ships in car factories. Same tools, same processes, completely different capabilities. This approach could make quantum computing as ubiquitous as classical computing, with quantum processors in every device and quantum capabilities in every application. But here's what I've learned from studying this field. The future isn't about choosing one approach over another. It's about hybrid systems that combine quantum and classical computing. Think of it like a Formula One racing team. You don't just have the race car, but also the pit crew, engineers, strategists, and weather experts, each doing what they do best. Hybrid quantum systems work the same way, with classical computers handling control, error correction, and user interfaces, while quantum processors tackle problems that are impossible for classical systems. And this isn't just theoretical. Companies are already using hybrid systems to solve real problems, from optimizing delivery routes and designing new materials to improving financial models and discovering new drugs. The quantum revolution isn't about replacing classical computers. It's about giving them superpowers. Now here's something that really excites me about the future of quantum computing. Companies like SpinQ have built real quantum computers that fit on your desk. These aren't toys or simulators, but fully functional machines that work at room temperature, cost less than a luxury car, and can teach quantum concepts to anyone. Imagine learning to drive on a real car instead of just reading about it. That's what desktop quantum computers do for quantum education, letting students program real quantum algorithms, experiment with concepts, and discover things that textbooks can't teach. This is how technological revolutions really happen, not in corporate labs or government facilities, but in classrooms and garages, where curious minds can play with the technology and discover new possibilities. The quantum revolution will be democratized, one desktop quantum computer at a time. Let me tell you about the quantum computers that are already solving real problems for real companies today. D-Wave took a different approach by building a specialized quantum computer known as a quantum annealer, designed specifically to find the best solution among millions of possibilities. Imagine trying to find the shortest route to visit 100 cities, while a classical computer would need to check trillions of possible routes. A quantum annealer can explore all routes simultaneously and identify the optimal one. Like having a GPS that instantly sees every possible path through traffic, construction, and weather to give you the perfect route. Companies are already using quantum annealing to optimize delivery schedules, financial portfolios, and drug discovery. And while other quantum computers are still proving they can work, quantum annealers are already delivering results. So here we are, 9 different approaches to quantum computing. And what my research has shown me is that they're all going to succeed. This isn't a race where only one approach wins. It's like the early days of transportation, when we didn't choose between cars, trains, boats, and airplanes, but used them all for what they do best. Superconducting systems deliver raw quantum power. Trapped ions offer precision. Photonic systems enable communication. Neutral atoms provide accessibility. Silicon qubits allow for mass production. And hybrid systems make practical applications possible. The most exciting part is that these technologies are starting to work together. Quantum networks are connecting different types of quantum computers, and hybrid systems are using multiple quantum technologies to tackle different parts of the same problem. The future of quantum computing isn't about choosing sides. It's about orchestrating all these technologies into something greater than the sum of their parts. When I first started researching quantum computing, I assumed it was just about building faster computers. But I was wrong. Quantum computing is about creating machines that think in fundamentally different ways, able to explore multiple solutions at once and tackle problems we never thought possible. The most exciting part is that we're not just building one kind of quantum computer, but 9 different types, each with its own unique superpowers and each solving different pieces of the puzzle. This means drug discovery that once took decades could happen in years. Weather prediction could become incredibly accurate. Artificial intelligence could reach new heights, and we could design materials with properties we can barely imagine. What excites me most is that the most important applications of quantum computing haven't even been invented yet. Just as no one foresaw social media when the internet was born, we can't predict the amazing things people will do once quantum computing is accessible to everyone. The quantum revolution isn't coming. It's already here, and it's going to be incredible. Thank you.